everybody. I'll be introducing FEM. So my name is Azuri. I'm the Vice President of Female Engineers at Monash. So what does FEM do? Well, we primarily seek to empower women identifying engineering students and create a supportive and inclusive network between students and professionals alike. So yes, it's a club for all of you to join. We do value male allyship because it's important to achieve gender diversity and inclusivity in engineering. So we do provide a variety of events, including academic, social, and industry events. We actually have a couple of big events coming up this semester, our Power Tools workshop, which hopefully will happen after this lockdown ends, and our industry guide launch, which will happen near the end of semester. So if you are interested in any of those events, do feel free to like our Facebook page to keep up to date. Someone from FEM will hopefully link that in the chat. And also we do provide exclusive events and discounts to our members as well. So if you are interested, feel free to sign up and become a member on the MSA Club's portal. But yeah, that's it for my quick introduction of FEM. I'll pass it on to MDN to introduce themselves.
Hey everyone, Monash Deep Neuron is a student team dedicating to empowering students and researchers to use artificial intelligence and high-performance computing through ethical, hands-on research projects. We engage with and educate the community through outreach events like this workshop in order to promote the accessibility and awareness of AI and high-performance computing. In the spirit of education, we've organized this workshop in collaboration with FEM, so all of you can personally go through and see how to create models for really, really cool deep learning projects. Hope you enjoy.
All right, so before we get started, I'll just do like a quick introduction to the workshops and the why, and also a bit of the logistics stuff. So MDN and FEM have teamed up to expose more women identifying and non-binary students to the world of AI and deep learning. We're going to have 3 workshops across the 3 weeks. So this week is the one in O week, then week 1, week 2. As you can see, the dates and the workshops are out on the slides. We have paired the technical content from the Deep Neuron team with some social education topics from the FEM side to help you learn some practical deep learning skills, as well as gaining a better understanding of the current landscape of women in AI and why we desperately need to improve the representation and diversity in this sector. All right, as you can see, the first workshop today is just a general introduction into deep learning, as well as a snapshot of women in AI in general. Our next workshop next week will be on layers, models, and techniques, plus improving minority representation. And last but not least, our final workshop will be on the applications of deep learning, as well as the ethics of AI technology. So let's get started. All right, so we are starting off, as I said, with a current snapshot of the climate of women in the AI industry. The future of smart tech. We can all agree that our lives are dominated by the digital world and that AI and smarter, faster technology is in our future. But who is in charge of this rapidly developing sector, and what does that mean for us? Here's some current statistics about the general landscape of the AI industry. As you can see, 12% of leading machine researchers are women, 22% of jobs in AI are held by women, 15% of AI research staff are women at Facebook, and 10% of AI research staff are women at Google. As you can see, there is a huge discrepancy across the whole tech industry. And if these are the percentages that you can see across the board, you can imagine how small it is when it comes to leadership and role model positions where real change is enacted. So what type of issues does this lack of diversity and representation cause, especially for machine learning and AI tech? The simple fact is our technology should be representing how diverse and rich the human race is. This lack of representation means that the creators of our technology often do not reflect all the people that the technology will be used for. This can create a lot of social disadvantages, especially for marginalized groups. AI tech often forms the basis of most of our current day-to-day systems. For example, companies can use algorithms for hiring candidates, or it is even present in something as simple as Google Translate. We will be discussing the effect of data bias and representation in deep learning further in our next workshop. So I'm not here to make everyone feel bad about how bad it looks in the industry. So let's have a look at some prominent and inspiring women currently paving the way forward in the AI field. First up, we've got Mia Shah-Dand. She is the CEO of Lighthouse 3, a research and advisory firm based in Oakland, California. They advise large organizations on responsible innovation, especially in regards to AI. She is also the founder of the Women in AI Ethics Initiative. And she also hosts monthly online events to help raise awareness on diversity on these fields and bring more awareness to BIPOC individuals within the industry. Next up, we've got Timnit Gebru, who is a computer scientist who works on algorithmic bias and data mining. She is also an advocate for diversity in technology and the co-founder of Black in AI, a community of Black researchers working in artificial intelligence. Timnit was most recently a research scientist at the ethical AI team at Google. But however, she was fired from Google after she co-authored a research paper highlighting the risks and potential biases of large language models, which form the core of the search engine's functions. This move brought a lot of criticism towards Google and highlighted the importance of having more diversity, not only within the industry itself, but also within those coveted leadership positions and boardrooms where decisions are made. As a co-founder of the group Black in AI, she works to increase diversity in the field and reduce the negative impacts of racial bias in training data used for human-centric machine learning models. Next up, we've got Joy Buolamwini. She's known for her groundbreaking work on racial and gender prejudices present in facial recognition systems. She is most known for her research project called Gender Shades, where she was able to point out these prejudices impacting the function of various facial recognition systems. We will be talking more about Joy's research in our next workshop as well. She has also founded the nonprofit, the Algorithmic Justice League, which works to raise awareness about the impacts of AI, equip advocates with empirical research, build the voice of the most impacted communities, and inspire researchers, policymakers, and industry practitioners to mitigate AI harms and biases. Last but not least, we've got Fei-Fei Li, who is one of the most influential scientists for AI in the 21st century. She pioneered the ImageNet project, which is a large visual database that forms the basis of current AI and deep learning technologies. On top of her incredible research work in the field, she's also an advocate for positive AI and in creating technology that helps everyone, not just a select few. Much like the other women that we have talked about, she has also co-founded a nonprofit organization called AI for All, which is dedicated to boosting diversity and inclusion in AI education, research, development, and policy. She works to bring underrepresented youth, including girls, people of color, and people from economically disadvantaged backgrounds, to the campuses of Stanford and UC Berkeley. So as you can see, this is just a really quick snapshot of some of the prominent women who are paving the way forward in the AI industry. So what now? These issues aren't solely present within the industry itself. They're actually symptomatic of a much bigger problem. You can even see these diversity discrepancies within uni itself. Even the Deep Neuron team, who is here with us today, has struggled to improve their diversity within their team. And this is exactly why we are running this series of workshops. We are hoping to provide this opportunity that many of you may not have had before to learn about AI and play around with some of the more technical content revolving around deep learning and machine learning. Hopefully this section of this workshop has inspired you and gotten you excited to dive right into it. Now I will be passing it on to Jason, who will be running through the introduction to deep learning and hopefully getting you guys to do something exciting.
Hey guys, I'm Jason and I'm here from Deep Neuron. And as we've already said, today we're going to run through basic introduction to deep learning using fast AI. So today we're going to cover a few main topics. So first of all, we're actually going to talk about what is deep learning, because you might have heard about it before, but what exactly is it compared to like AI and machine learning, stuff like that, and run over some applications. Then we'll talk about some deep learning concepts and deep learning theory. And finally, at the very end, we'll move on to an actual practical image classification task you guys can run through yourself using fast AI. Okay. So first, a quick background into AI and deep learning. So artificial intelligence as an academic discipline was founded in 1956 after a number of advances in the field, with the first neural net machine developed, the SNARK, and also the Turing test. However, the broad definition of AI covers really any device that in some way can mimic some kind of cognitive function. So from there, we have a subset of AI, machine learning. Machine learning came around in the 1980s and is used to identify any algorithm that can take in data, learn from that data, and then apply what they've learned to make some better decisions. It was really reborn due to the rediscovery of backpropagation, with powerful hardware becoming more accessible, which we'll get into in a bit. And so then we have another subset of machine learning, deep learning. So deep learning is used to describe an algorithm that contains a large artificial neural networks. These models are designed to continually analyze inputted data with some kind of logic structure, very similar to how a human would draw conclusions. They're very much modeled around the brain and brain function. The term deep often refers to the number of layers, so the very high number of layers involved within a neural network. So deep learning has really only surged in the 21st century, once again, due to our access to more and more powerful hardware. So it used to take weeks, if not months, to train even a really simple neural network. So advancement in computing technology has really allowed a group like ours to excel. Here's a quick meme about the struggles of deep learning. All right, so for some quick examples of where deep learning can be used, on the left, you can see basically a camera that can identify different objects and animals that are in a single frame. And on the right, what we have is we have an image from the Tesla automated driving system. So like a self-driving car, which can identify in real time where they are on a road with respect to their surroundings. So you can see from this image that it can identify different people, where cars are, where the road are, where signs are and stuff like that, and segment it out very well. All right, so before we go any further, I want to run through a couple of examples of some online AI demos just to show you what some of it's really capable of. So can I grab the screen share real quick?
Yep.
All right, so this first example is basically a quick example, an example of an AI that's been trained on people drawing kind of like short little doodles, and then an AI's tried to learn to recognize what they're actually drawing. So as you can see, this is a tough one. So we want to draw a knee. We might draw like kind of a leg shape, and really quickly, the AI can pick up on what's going on here. So you have something like a birthday cake. So what you can find is a lot of these drawings, from how much data the AI has learned from, it can learn pretty quickly even with a really rough sketch, as I have here. I'm not sure if it's going to be good enough for it. So even though my drawing is really bad, of course, it's learned from other people as well, whose drawing is also pretty bad. So it gets pretty good at recognizing these images. Another example is this one, which is an AI that's been trained to autocomplete sentences. So what you can do is you can write something. So today we're going to learn about deep, some kind, and then we'll let it autocomplete and see if it can actually come up with something good. So today we're going to learn about deep learning, the field of artificial neural networks that are used to solve real world problems such as machine translation or facial recognition. It's pretty good so far. As you can see, it's just generating all of this based on today we're going to learn about deep. And then from there, it's managed to create almost an entire sentence and a half. That's, you would expect, if you read this as a person, you say, oh yeah, another person's written this. This seems very reasonable. All right. So all these examples are also in the slides, and I definitely encourage you to run through them in your own time to see really what these machine learning models are capable of. Okay, so let's get into, machine learning is a really broad field, of course, as you would assume, but we can break a lot of it down into three main areas. These are supervised learning, unsupervised learning, and reinforcement learning. However, I just want to warn you to be aware that these are really broad fields that aren't entirely separated. They all have some overlap, like semi-supervised learning, which is basically a combination of supervised and unsupervised learning. So, supervised learning algorithms are generally applied to data sets that are labeled, meaning every piece of the data has some label. For example, if you had a data set of images of different things, say you had images of cats, images of dogs, cars, airplanes, and so on, the labels would be what class the data belonged to. So if the image was of a cat, its label would be cat. And if it was a car, its label would be car. So supervised learning has labeled data. And when training our model, we provide direct feedback to our model to tell it whether it's doing a good job based on these labels. Our hope then is that our model then can make some prediction about the data we fed into it. So based on this description of supervised learning, we have labels and we get feedback, and we might use it for images. Does anyone in the chat, throw it in the chat, or feel free to speak, put your hand up. Does anyone have any ideas about what we could maybe use supervised learning for? Some like cool applications we might have for it. If you have an idea, just type it in chat, feel free to speak or whatever. Linear regression, image classification, disease, yeah, all of these are really, really good examples of what we use it for. All right, so I'll run through a few of them. Linear regression, yes, I'll talk a bit more about that next slide. Image classification, definitely. Image classification is a really common one to find. Object identification, exactly like in the first few slides. Disease detection, object detection, capture. Capture is a really good one. So what's with capture? When you do captures nowadays, and you still have these image ones, you're actually training. You're actually creating a data set, say for Google. So the capture will get you to label something. So it will say, what are these numbers in these like signs, or click pictures of buses or something like that. And so it'll first give you a really, really easy ones that the machine can do. And if you're good at those, it will give you ones that the machine learning model doesn't know. So what you're doing with captures is you're basically labeling data sets for supervised learning for Google. Predicting house prices, yep, facial detection. So yeah, all of these are really good examples of supervised learning. So we generally use supervised learning for classification problems or regression problems. regression problems like we talked about. So a classification problem generally involves predicting basically a discrete value from the input data. So in the example I gave before, we might train our model on images of cars, dogs, cats, etc., to recognize what's in these images. So is this an image of a dog, a cat, a car, or whatever? Then, if we gave our model a picture of a car, it's like a new car that hasn't seen before, the model should hopefully be able to classify this as an image as a car. So, of course, this would be a classification problem, predicting the label of the image, basically. In the practical task we'll go through today, we'll be going through a classification problem where we'll use a model to take photos in from the data set and classify these images into a labeled category, similar to what I'm going to talk about a lot because it's a really good example. So then we have regression problems. A regression problem instead tries to predict continuous values. For example, a regression problem might be, say you have a bunch of pictures of faces. From there, you might give it to the model and try and teach the model to predict certain features such as age or height or weight just from these images of faces. Because these are all continuous values, this will be a regression problem. And so as you can see on this slide, we have a few examples of supervised learning. All right. The second type of machine learning is unsupervised learning. Unsupervised learning is different from supervised learning in that the data we train our network on isn't labeled. So because we don't label our data, we don't actually give feedback to a model based on labels. So it's a bit more abstract, but the purpose of unsupervised learning is then to try and find these basically hidden patterns in the data. We might be able to find, we might be able to use the patterns our model finds to do things such as generate new data. So for example, if our model can learn the underlying structure of a bunch of different images of faces, we could generate brand new faces based on the structure. Or we could do such things as, in a bunch of images of faces, what defines having glasses on? If we can learn what defines having glasses on, we could theoretically add like glasses to pictures of faces that don't have them on. So with all that said, this one's a bit trickier, I think, but do you guys have any cool ideas of things we might be able to use unsupervised learning for? So password generators, yeah. GPT-2. Generating cat images, yep. Clustering of images, definitely a big one. Language models, yep. Learning how to play games, consultation, yeah. So again, these are all really cool, some really cool ideas coming up. On this slide, we have some examples of some really cool things done with unsupervised learning. So the top one, as you can see, is basically that the model has learned to colorize images. And so it's tried to colorize an image of a Golden Gate Bridge. This is pretty cool. But you will see it's white in the picture. I think, if I remember correctly, the bridge was actually still red at this time. So it's not always perfect, but it's really good, as you can see. The bottom left there has these images of faces. As you might get from the word there, or from the phrase there, these people don't exist. These are completely newly generated faces from a model, which, of course, to me at least, if you looked at them, you could totally see them existing. And finally, we have in the top right corner there, this GIF that's just been fully colorized from a black and white GIF. All right. So now we come to the third type of machine learning, which is reinforcement learning. So reinforcement learning is more the study of how an AI will make a decision and learn from these decisions. So the AI's goal is to make decisions that give it these rewards, and then to maximize the rewards it gets in an environment over time. So for an example of reinforcement learning in the real world, think of how you might train a dog by saying sit. And if the dog sits, you might give it a treat. So what you're doing is you're rewarding the dog for taking a positive action. So the dog is more likely to sit in the future when you say sit. it's a pretty similar principle for reinforcement learning. So any ideas what we could use reinforcement learning for? Because this one I find is really cool. Yes, there's some really good ones here, and some really awesome ones, I think myself. We have robots that can learn with deep learning, with reinforcement learning. Reinforcement learning models can learn to play video games, buying stonks, yeah. Solving optimization problems. I'm not actually not 100% sure on that one. I'm not the best on that. What's the difference between reward and RL versus direct feedback and supervised learning? I probably can give you the clearest definition. I think someone hopefully will be able to answer you in the chat with like a better definition than I could give. All right, so these are some of the examples, the really cool examples of reinforcement learning that for me myself got me into deep learning. So we've got the classic OpenAI 5 that learned how to play Dota and could play Dota better than any pros could, really. We have AlphaGo, which learned how to play Go, which is a really, really hard game for machine learning models to learn because it's got so many diverse states and instances. And of course, it beat the best in the world. And then we have Mario, which is a reinforcement learning model that can play Mario. So we'll also go a bit more into the fundamentals of reinforcement learning in the third workshop. So stay tuned for that. All right. So to summarize, supervised learning is when we learn based on a labeled data set, giving feedback with the goal of predicting something better data. Unsupervised learning is where our data doesn't really have labels and we don't give feedback. We really just want to find the hidden structure in the data. And reinforcement learning is where we'll have an AI that makes some decisions and learns from these decisions based on the rewards we give it. All right. So we've already covered quite a bit. So I just want to quickly see if there are any questions so far about the different types of machine learning in particular. I think there's already been a couple. Feel free to chuck them in the chat or ask over voice. And again, if you have any questions, as I've seen so far, it's really good. If you have any questions at any time throughout the talk, feel free to ask it in the chat and people will be more than willing to answer it.
Yeah, man, I've got a question real quick. With the unsupervised learning, how is the AI learning?
So how does it learn? Okay, so I'll use the model that I work on as an example called an autoencoder. So what it does basically is it takes a bunch of images as inputs and it tries to shrink them. So it says, can we describe these images with like 10 or 20 numbers? So these numbers might represent features of a thing. So if it was, say we were taking images of cars, maybe it's like, this is a wheel here. Is like, does it have wheels? Does it have, car-like features? What's its background look like? So you'll take an image, which is like 100 by 100, so like 1,000, 10,000 pixels. Shrink that down into 10 numbers. And then we'll have another model that tries to recreate it from this really small set of like 10 numbers. So from there, and basically our goal is to try and get a really, really good reconstruction. So our model should be able to recreate the images really well. And so what we've done then is we've learned 10 numbers or whatever that can describe our image really well. And so we're learning some patterns based on that. And so from there, you can say, compare the images. So if you had a face with glasses, a face without glasses, take the difference of this small space describing the image. Now you've got what glasses look like, and you can use that to do generation and stuff like that. Does that kind of make sense?
Yeah, it does. Thanks.
Awesome. Oh, I've gone way too far. Okay. So next we're going to talk about some actual deep learning theory. How are we going to actually do deep learning? So in a deep learning model, we have 4 key ingredients that we're going to go over today to building a successful model. These include, first of all, we need a varied data set that has a large amount of data for the model to learn from. Data is by far the most important factor. As for deep learning, we need data and lots of it. The larger the data set, the better. Second, we need a model with an architecture suited to solve our required problem. We can either use a pre-trained model using transfer learning or create a complete network architecture from scratch. So for today's task, we're going to use an architecture known as ResNet34, and we'll also go through transfer learning in a bit more detail. Third, we need a well-planned training cycle. And fourth, we need a good evaluation of the model to determine if any more investigation or training is required. So let's start with the data set. All right, so first, a note on how we're actually going to, first a note on how we actually use images as inputs to our models. So our networks take numbers as inputs. And so we have to represent our image as a set of numbers to train our models on them. What we do is we represent images as these data objects called tensors. All right, to think about tensors, first start thinking that we could represent a black and white image as a matrix. So, a 2-dimensional set of numbers. Each space in this matrix would correspond to a pixel in the image, and the number would represent the intensity of that pixel. But for a color image, we don't only have one brightness, but 3. The brightness of the red, the green, and the blue channels to make a full RGB image. So how we represent this is we basically stack 3 matrices. So we have a red, a green, and a blue matrix, each one representing one of the 3 RGB channels. Both the matrix, so the 2D arrangement, and this 3D arrangement of stacked matrices are tensors. So tensors are basically just n-dimensional. So that means any dimension, such as 1, 2, 3, 4, arrangements of data. In this case, we're representing the black and white image as a 2D tensor and the color image as a 3D tensor. So yeah, so we have a question in chat. Could you just say tensors are just 3D matrices? So I wouldn't exactly say that. Yeah, yeah. As Will said, you'd say a matrix is a 2D tensor more than anything. All right, so we can represent black and white images with the 2D tensors, matrices. We can represent color images with 3D tensors. So with all that, does anyone have any ideas? Yeah, does anyone have any ideas what we might be able to use a 4D tensor for? Because they do exist. Chuck your ideas in the chat or speak them, feel free. Yeah. Yeah. So the one I like to think of myself is if we have a bunch of different images, we have a bunch of 3D tensors, and we stack, and we have a 4th dimension that is which image are we going through, stuff like that. Yeah. Awesome. All right. So we've talked about images, now onto the actual data set. So a data set's essentially what it sounds like, which is a set of data. We usually start with the data set when approaching a deep learning problem, as we want to build our model to accurately predict similar data that's going to be passed through it. Generally, we split our data set into 3 areas. First, we're going to have a training set. So this is a set of example data that's used for the network to learn. Second, we have a validation set, which is used to tune the parameters of our network. And finally, we have a test set, which is basically a set of data used only to assess performance of a fully specified classifier. So once we've fully trained the model. So what's the problem with just having one set to do all these, to train, validate, and test? What happens is, if we train the data on the same set of validation, we won't be able to tell whether the models actually learned, so this is the key distinction, whether the models learned from the data or whether the models completely just memorize the data. This distinction's key because when we're using deep learning, we want to be able to accurately make a prediction from new data given as previous training. If we've learned from the data, hopefully we've learned features and stuff like that, and we can recognize them in different images. But what can happen is if we train and validate on the same set, the model could have just memorized the data perfectly, which we don't want. It's not going to be able to do anything new with the data. It will work 100% of the time when we feed it an image it's seen, but if we feed it anything new, it will completely fail. All right, so usually we put our data set through a series of transformations, such as a modification of height, width, scale, color, or resolution. If the data is a set of images, we could also use a process known as data augmentation, which is a technique to artificially create new training data from existing. We're not really going to explore these techniques today, but they'll definitely be useful later on. All right, so that's everything about the data set of a model. We represent images using these data structures we call tensors, and then we split our actual data set into train, validation, and test groups. We then might also transform or augment that data as well. So before we go on, anyone have any burning questions about anything in this data sets section? All right, cool. So now on to what we've really been building up to, which is the model itself. Neural networks essentially form the backbone of deep learning. Their goal is to basically find an approximation of some unknown function. So think about the example we talked about earlier, where we might want our model to take an image and output whether it's a photo of a cat, a dog, plane, car, whatever. What our model aims to do then is, in this example, approximate some function that describes whether a photo is a cat, a car, or a dog, whatever. So it might take in an image and output a probability that it's one of these, something like that. So neural nets are made up of many artificial neurons known as perceptrons. The data is passed into the input layer, the first layer of the network. Then the outputs of the input layer go to the hidden layers, which do some work on the data and pass it onto another hidden layer and so on. Then they chain along. And finally, at the last hidden layer, the outputs pass to the output layer, which actually generates our final output data. Going back to our image classification example, this output might be, well, like I said before, a set of probabilities that the image is a dog, cat, car, or whatever. So this movement of data going from one layer to the next is called forward propagation. And we call these hidden layers hidden because we can't actually see what's being processed in there. We can only really see the input and output layers. All right, so let's dive a little deeper into the actual neural network theory and build back up to our fully spec'd out neural network. So the building blocks of the neural network are perceptrons, which are essentially just artificial models of how real-world neurons work. Perceptrons take in some inputs, which get processed in the nucleus, and an output is generated that can either be passed on to other neurons or to be processed further, or can actually just be considered the final output. So let's describe this a bit more mathematically so we can actually program these perceptrons and use them. So we start with a bunch of inputs that we'll just label as X. These inputs each get multiplied by a corresponding weight, which we've labeled here W. These weights are basically randomly assigned when we initialize the network. And as we train the network, these are updated. Over time, the network will assign a higher weight to inputs it considers important and a lower weight to unimportant inputs. So these weights are really where the learning's happening, where we're actually going to learn this hidden function we've talked about. So Then we take all of these input and weight pairs that have been multiplied and we add them all together. And the result of this addition is passed through a nonlinear activation function, which is labeled by the non-linearity here, which gives us the final output of our perceptron. All right, so let's talk a bit more about this nonlinear activation function, because it's pretty important. What this activation function does is it basically adds non-linearities to the network. So this is important because with most data, a linear function won't properly model the unknown function we want to find. So, for example, if we wanted to separate the blue pluses and the gray squares in this like diagram here, for the plot on the left, we can just do that with a straight line. So that's fine, right? For this problem, a linear classifier would be working fine because we can separate the data with a straight line, all good, very linear. But as you can see for the plot on the right, we need to draw this kind of circular ellipse shape with a bunch of different bends to separate the data. So this isn't clearly not a straight line, and a linear classifier would be completely terrible at solving this problem. So you need something very non-linear to get a good solution. In the real world, our data is pretty much always very non-linear, so much more similar to the one on the right. And so we can only do anything useful to it with very non-linear models of our own. So this is what these activation functions at the end of the perceptrons do. They basically introduce these non-linearities to the data that we would need to model real-world data. If we didn't have them, what would happen is our network would collapse basically into a really, really complicated linear classifier, which we don't want. It's actually just not going to model anything very well. So basically, these activation functions allow us to approximate complex nonlinear functions, and they're really what makes the network actually work and able to learn complex things. All right, so we've got our perceptrons. So what we can do now is combine a bunch of these perceptrons in parallel. Yeah, so what we can do now is combine a bunch of perceptrons in parallel to create what we call a dense layer. We pass inputs into all of these perceptrons and then pass the results all through an activation function. We get all of these outputs from the perceptrons in the dense layer, all in parallel. We can then put more and more dense layers together in series, so chain them together to finally build our full neural network. So the hidden layers are how we classify the neural net. So here we'd say the network is a single layer network because we've only got one hidden layer here, that red layer. All right, so just to make sure you guys are following, I want to see if you can tell me what all the letters in the picture on the right actually represent. Before you start to do that, I'll let you know that in machine learning, if we have a capital bolded letter in italics, like these W's here, what that's representing is that it's a matrix of some kind. So it relates that the matrices here relate to something we've talked about, but we haven't done it as a matrix before. It's just been numbers before. So can anyone let me know what's X here? What's X representing? It should be pretty straightforward because it's almost given there. Yep, it's an input. The tricky one, it relates to what we've done, what we've just talked about, but what could W be? So thinking about the perceptron we talked about before, what do you think W is? Yep, awesome. So yeah, W is a matrix of weights. We represent it as a matrix because it simplifies the math a whole lot. We can just use matrix multiplication to do this entire like propagation process. All right, a trickier one. What's Z? Yeah. So yeah, it kind of is in the hidden layer. It's like the result in the hidden layer. How I would almost think of it is, yeah, I would think it as Daryl said, it's like the sum of the inputs and weights. So once we've taken all our inputs and multiplied them by our weights and summed together, we have Z. Now we have G of Z. What's G going to be? Yep, awesome. the activation function we talked about, really important that's there. And finally, what's Y? Yep, output. So that's really good because this really is all the basics of your fundamental neural network. You can chain more and more hidden layers together, but it's all going to be the same. You're going to have your inputs, weights, activation functions, and outputs. All right, so let's move on to the loss function. So basically, the loss function will measure the accuracy of our network and basically quantify how well our network's doing. Essentially, the loss function is a measure of the difference between the predicted values and the actual values. And it will basically try and penalize the network when it makes an error. As we train the network, our goal is to increase the prediction accuracy and reduce error. So we want to minimize the loss, basically. For example, referring back to the image classification example I keep going back to, if the model labeled an image wrong, so it labeled a dog as a cat or something like that, it would cause a high loss, while a correct prediction would cause a low loss. So the diagram here is a simple example of the loss function. W represents a weight and J represents the loss function. In reality, of course, as you'd assume, we have hundreds or thousands of weights, but for the sake of it actually being able to visualize it, where in this diagram, we're only dealing with one weight. So our aim here is to find the global minima of the loss, which will give us the most accurate model possible. So what we want to do basically is to change our weight values such that we can get to this global minimum. All right, so we had our one weight example, and this is an example of what a loss function would look like if you have two weights. The multicolored surface here is our loss represented by J. So we can assume that our weight initialized to the cross on the red peak of the landscape, which has a high loss value. In this case, our global minima is in the dark blue valley, which is basically where we want to move our weights to. All right, so we have a question. Do we know the loss function beforehand? So the loss function is something that, the loss function is something that you would choose in training. So yeah, we would know our loss function beforehand, which is how we're actually able to optimize. Okay. So this was a pretty big section and we talked about a lot. So we've talked about some of the main points in our deep learning models, specifically neural nets in particular. So the main things I hope you can take away from all this stuff I've talked about is that, first of all, we can model neurons mathematically using these things called perceptrons. These perceptrons have non-linearities so that we can approximate non-linear functions, which is what most real-world data is. We can then combine these perceptrons in parallel to make a dense layer and string these dense layers together in series together to make a neural network. And then we want to measure how well our network is doing, as we use a loss function. And we want to minimize this loss for the best results, which is what we'll get to in training. So before we move on, any questions?
Yeah. How do you determine the loss function and activation functions?
Yeah. So in general, these are things that we've pre-chosen. So we've pre-chose. It really depends on the problem as well. So the loss function is very problem dependent. Your loss is going to be very much defined on like what you want to optimize. So for the example I gave you before about reconstructing the faces, our goal is like reconstruct the face. Our loss would be the difference between the original and final, like the mean squared error. So like the loss, the difference between the two faces basically is the loss. And we want to choose loss functions that we can differentiate for reasons we'll get into. And the nonlinear activation functions, there's a few different ones. It normally just collapse. Yeah, there's basically a few different pre-chosen ones. Again, someone else might have a bit better explanation in the comments. I'm not sure.
Yep. Thanks, Ryan.
All right, so in this third section now, we're going to look at training our model. When we train our model, we want to minimize our loss, as I've just talked about. To do this, we can use one of a bunch of different optimization methods, which we have listed here. The simplest one, though, is gradient descent. And this is the one that we're going to look into a bit today. All right, so once we have the neural network and we begin training, we can perform gradient descent to minimize the loss. In gradient descent, we basically calculate the gradient of our loss function at the current point we're at on the loss landscape. We then want to move in the direction of steepest gradient so that we can hopefully move towards the minimum. In this example, we would calculate the gradient at our initial position, so that's given by the dotted line. We'd take a step to the left in the direction of decreasing gradient, recalculate the gradient, take another step, and so on, until we hopefully reach a point where our steps always send us to the same place, which is the local minimum. What we actually do by taking a step is we basically adjust our weights to some new values we step to by gradient descent. The hope is that this local minimum is actually the global minimum. Not always the case, of course, but it's the hope. So that theoretically we found the best model we can have. How far each step sends us is determined by the learning rate, which we'll talk a bit more about in a bit. All right, so going back to the loss function we had before, in this case, we have two weights now, and our loss function is clearly a lot more complicated than just our one nice local minimum. But we can still apply gradient descent in the exact same way as before. For this example, we can think about gradient descent as almost like climbing down a hill defined by the loss landscape. What we want to do is we kind of want to take small steps and walk down the hill instead of just jumping down the hill all at once. If we start from a certain point and we slowly move down the hill, we can hopefully keep going until we reach the very bottom. So, because the thing is if you don't know the entire loss landscape. If we did, we could theoretically just jump all the way to the bottom. But we don't actually know that. We only know our local gradient. And so if our step is really, really big, it can come into problems, which I'll get into next slide, I think. So on this diagram, the plus symbols on here is the model learning from the weights it currently has. Again, we can calculate the gradient based on our current weights and update our weights based on the gradient. So how this works is that our error, along with the gradient, basically flows back from the output to the input through the hidden layers, and the weights are updated in a process we call backpropagation. So the learning rate is the rate at which we descend towards the minimum, so the size of the step we take. As you can see from this diagram on the right, if we have a learning rate that's too high, we could just end up jumping around the loss landscape and never converging to a minimum. In fact, in this diagram, where our learning rate is actually just making the problem worse. So this is why you need a very good learning rate. It has a very big effect on how well your model is trained. But the exact amount you choose to go down at once is pretty complex and problem specific. It's generally way too complicated to determine this value, but there is a nice method to choose a reasonable starting point that we'll go into a bit later. Okay, so that's the basic concepts involved with training a model. This is all a lot of content that's coming at you pretty fast, so I just want to again give you a quick overview of what I hope you can take away from this. So first of all, we can optimize our models with a bunch of different optimization methods. A simple optimization method is gradient descent, where we basically calculate the gradient and use backpropagation to change our weights to slowly move down the loss landscape. The amount we step each time is determined by the learning rate. All right, any questions on anything about training? All right. Okay, so finally, we're going to move on to evaluation. So first, let's define an epoch. An epoch is defined as a single training iteration. In one epoch, we're going to do one forward pass and one backward pass, like we've talked about, for all of the input data. Generally, the number of epochs you choose to train with impacts how accurate the network is and how well the model fits to the data. So here we've got, how do you train your model? Like step by step. Okay. So the question is, how do you train your model step by step? I'm going to be honest, I couldn't tell you exactly. It has to do with like taking partial derivatives and updating your weights based on like the gradient. But when we actually do machine learning in code, a lot of that's abstracted away for us by the libraries. So yeah, I encourage you to go look up the math yourself, but it just has to do with like updating weights based on like derivatives and stuff like that I'm definitely not going to go into in this workshop. All right, so so coming back to epochs, here we've got our plot of loss versus the number of epochs trained. So you can see what happens is that after a few epochs, the losses really rapidly drops and then begins to stabilize a bit more. As we continue to train for even more epochs, our training loss tends to go down, but our validation loss is actually going up. This is basically showing that training for more epochs can give a higher accuracy, but training too much can lead to problems like overfitting, which I'll talk about very soon. All right. Generally speaking, in fast AI, you're going to notice two types of losses. You're going to notice a training loss and a validation loss. The training loss is the loss experienced through training, and the validation loss is the loss experienced when we evaluate the model from our validation set. The validation loss converging is usually a pretty good indicator that your model is also converging to its optimal performance. Because, yeah, we've been training on our training data, and validation data is not our training data, so it's a better indicator of how well our model's doing. All right, so when the accuracy of our model becomes really high on our data set, and we find that on a similar data set, our model seems to be much less accurate, which is kind of what we saw before, we can conclude that our model has become overfitted to the training data set. So overfitting is a modeling error that can occur in statistics when a function is too closely fitted to a set of data. So as can be seen in the images below. So on the left, we have a function that's been fit to the data points very accurately. It's displaying the proper general trend of the data. Whereas the function on the right has fitted so well that it's taking into account every single little deviation in the data. In deep learning, our models tend to overfit when they've been overtrained on the training set. The deep learner has to recognize, hopefully, when a minimum of loss is occurring and hopefully aim to stop the training before the data becomes too overfit to the model. Overfitting can also be reduced by training the network on more examples and by also changing the complexity of the neural network architecture. In chat we have, is this where we draw the example of how an AI might memorize answers rather than learning? Yes. Yeah, exactly. So a quick low-res meme about the problem, the struggle of overfitting. All right. So when something goes wrong and we're getting basically less than ideal results, it's really important that we can see where the model failed. Often when a model fails, it's due to problems with our data. As I said before, data is really, really important to machine learning. This can include wrong labels, low quality images, or just hard to distinguish images, because often your data sets aren't perfect. Two methods that we can use are the confusion matrix and top losses, which you'll see in the practical example today as well. So here we've got an image of a confusion matrix for an image classification problem. Very similar to the one I've been talking about today with dogs, cats, planes, cars, and stuff like that. The rows represent the actual labels, which you should be able to read on the slide just, oh, it's a bit faint. And the columns represent the predicted labels. The numbers along the central diagonal are then, based on this, are images that have been classified with their correct label. So for example, we have 973 images that are airplanes that have been classified as airplanes and stuff like that. So anything not on this diagonal is an error. We can see that a common error is basically classifying a dog as a cat and a cat as a dog, and vice versa. This isn't too surprising, as this data set's pretty low res. This is the Sci-Fi 10 data set, which is the one you work on today. And cats and dogs are both four-legged animals that if you blur them, you could see how even humans could make mistakes on which one's which. All right. So that's it for the last section of deep learning theory, which is evaluation. I'll quickly summarize everything from this section, and then we'll go into breakout rooms and have some time to discuss and basically digest everything I've gone through so far. So first of all, we learned that an epoch is a single forward and backward pass over the entire data set. Second, overfitting is when the model fits too well to the specific data set and can't transfer its training to any new data. I'll mention as well, this loss versus epoch graph here, as I think I talked about it before, is an example of overfitting occurring. As you can see, the training loss is still falling as we'd want it to, but our validation loss is increasing. And thirdly, we can use different metrics to try and spot what could be causing problems in our data, such as top losses or a confusion matrix. All right, I won't ask questions because now we're going to go into a discussion time for, I assume, the next 10 or so minutes at this point, just so we have time for the practical at the end. In the slides, there's a few questions that you might want to go through if you have a link to it, I'm not sure. Yeah, there's a few questions. If you have any questions, feel free to ask your demonstrator. If we'll be coming around and stuff. Hopefully we can get an answer to your question.
Is everyone in a breakout room?
Breakout rooms are open. Feel free to join in. Just to all the extra people in the main room.
Renoli, would you be able to make Zuri and myself co-hosts, please?
Yep.
Theory behind it all. But now we actually get to the exciting part where we can actually use deep learning. So for today, we're going to use a Python library called FastAI. FastAI is arguably probably the easiest deep learning framework around, and it's a really great resource to get started in, as you can complete a classification problem in basically 5 lines of code. So FastAI is able to take some of the heavy lifting away from people getting started. However, we've sprinkled in some concepts that we have learned about today to hopefully try and reinforce these ideas and start to build your intuition regarding deep learning. Generally, we're not trying to reinvent the wheel every time we use deep learning. We want to build upon the knowledge of others by taking an almost complete model and finally tune it towards the end to fit it to our problem. So a bit of info, Fast AI is built upon PyTorch, which is an open source deep learning framework that we're going to get into a bit later in the workshops that allows you to go a bit deeper. All right, so for this workshop, we're going to use Google Colab, which is basically allows you to run Python code in like a notebook style in your browser. And so you can train your deep learning models all in the browser. All right, so today we're going to do an image classification task using the Sci-Fi 10 dataset, which is basically a dataset of about 60,000 images. So in this task, you should just work with the dataset, look at the model, work with the training and evaluation. I'll just quickly show you the workbook and how to get started after I go a bit through transfer learning, and hopefully everyone will get the chance to train their own models. All right, so today we're going to use a form of transfer learning that is known as inductive transfer. This is where the scope of possible models is basically narrowed in a beneficial way by using a model fit on a different but related task. This allows us to reuse a model that's been pre-trained for us as a starting point, saving both time and compute power. It also doesn't require us to develop the network architecture that could just end up being worse than a pre-trained model anyway, because this could have been trained for months, whereas we only have, an hour or so to really train it. Okay, so we're not going to explain how CNNs work in this workshop, as we're going to go into them in the next workshop, I believe. However, we'll use them today for the image classification problem to basically show how neural nets can be used in prediction problems. The model we'll use is known as a ResNet model, specifically ResNet 34 is one we're going to use today. All right, so can I have this share again? Because I'll go through the notebook. Sorry. While we're doing this, I think, so there should be a link. Do we need to put the link in the chat, or just to have slides, the link to the notebook? When you follow the link, that's, I'm not sure, it'll be in the chat or in the slides somewhere. We have this, so we have a few things to do to get started. First of all, to make your own copy to save for your own future use, you can click on File, Save a Copy, or no, not GitHub, Save a Copy in Drive. So this will create your own copy of the notebook. And then from here, you want to make sure to follow this. You want to go to runtime. You want to change runtime type. Make sure this is set to GPU. Yeah, I'll emphasize this again. Make sure you follow this save a copy in Drive. It's really, really like, otherwise you're changing the original copy, and that's like no good. So yeah. So make sure your runtime is, make sure your runtime set to GPU. If it's not, the model will take so much longer to train. GPU accelerates it so much. So we've got the sections on dataset, on the model setup, on training and validation. In breakout rooms, go through it all. You have the option to run all. This will run all the cells for you, and it will stop here. So the thing in this notebook to do is to go through, hopefully discuss with the demonstrator and make sure you understand everything that's going on, and then set your base learning rate by, you can take the learning rate find by this command, learn.lrfind. You can take the learning rate that's found, or try and tune your learning rate to get a good one. So change that to a bunch of different values. I'll let the demonstrators go through it more in the breakout rooms now. All right. So the point of that last evaluation activity with regards to the learning rate was for everyone to really hopefully get an intuitive understanding of how the learning rate can impact the accuracy. The answer to what's the optimal learning rate, well, it's still incredibly complex and problem dependent. But generally speaking, a good estimate for a starting learning rate can come from the point at which the greatest change in loss occurs on the descent to the minimum. So what I mean by this is that the learning rate at the steepest point of descent on the graph, so the steepest descending gradient, is generally a great point to start, as it's the point where the loss is improving the fastest. So before we finish up today, I just want to quickly, to be like a little over time, quickly summarize the main points of everything we've gone through today. And after that, we'll take any more questions you might have. All right, so types of machine learning. There are 3 broad categories of machine learning that have some overlap. These are supervised, unsupervised, and reinforcement learning. With supervised learning, we're going to use a labeled data set. With unsupervised, we use an unlabeled data set. And with reinforcement learning, we have an AI make decisions and learn based on a reward system. There are 4 key ingredients in deep learning that we cover today: the data set, the model, training the model, and evaluating the model. We represent images using tensors that we've talked about, and we split our data set into train, validation, and test groups. We then might also transform and augment the data set as well. And models, specifically neural nets, are made up of these artificial neurons called perceptrons. These perceptrons have non-linearities to allow us to model non-linear data. We can combine a bunch of perceptrons to make our full model, and we measure the performance of the model using a loss function that we want to minimize. In training, we want to minimize our loss. We can do this using optimization methods, the simplest of which is gradient descent. In gradient descent, we calculate the gradient to slowly step down the loss landscape to reach a minimum loss, which is hopefully a global minimum. How far we step is determined by the learning rate. And finally, we train our model for several epochs, where one epoch is a forward and backward pass over all of the data. Then our models can overfit if it trains too much on data that it learns to recognize exact images instead of general trends and features. And finally, we can use different metrics to try and spot what could be causing problems in our data, such as top losses or confusion matrix, which hopefully you learned a bit about in this practical. All right, just before we finish today, I just quickly want to mention this glossary of machine learning terms. That can be really helpful if there's a specific term that you've either heard here today that didn't quite click with you, or even if you've heard another term before and didn't really know what it meant and just wanted to learn about it. It's got a lot more than just what we covered today though, so be careful. It's definitely not needed that you go and look through all the terms. It's just really there as another resource that you can look at to help you learn a bit more about machine learning. So, thanks for listening. This has been a lot of content and you guys seem to have gone really well through it all. So that's really awesome. Next, I just want to mention quickly, next week, we have a workshop on layers, models, techniques, and also from FEM, improving minority representation in the industry. There are some extra resources if you are interested that you can look at for the next workshop. And before you go, please fill in our feedback form. It really, really helps us to make this better in the future. Thanks for listening.
Thanks, guys.
Thanks for coming.
Thanks, everyone.
By the way, MDN and FEM members, did we want to debrief very quickly now?
Yep, maybe a couple minutes, and then
Sorry.
I think everyone's gone.
Stop the recording.
Yeah, I think pretty much everyone's gone.
Is Anson?
Yeah, that's the only person that was wondering about.
I don't think they're in the meeting because they've just been like that the whole
Oh, yeah.
session.
Well, they're out now.
Yep.
So what do we think?
Wait, do I start recording?
Who started the
In
recording?
the breakout room.